Yeah, thanks everybody for coming. I don't think it needs a long introduction. HaJEDyahLZY is here again. He's becoming a regular visitor here at Google and specifically in Santa Monica, helping us with our work on applying his adiabatic algorithm to problems in machine learning. But Eddie will talk today about a new passion of his, which is quantum money. So looking forward to this talk.
Okay, thank you. Can everybody hear me? We're okay remotely? Okay, thank you. So I'm going to be talking about quantum money. And this is a project that I've worked on with my students, David Gossett and Andrew Ludomirsky, and postdoc Avinatan Hasidim, and Peter Shore, who is not a student. He's a very well-known guy in the world of quantum information. And let's see if we begin. I guess I don't know how to advance. I guess I have to go here to advance it, huh? Okay. So this talk is about quantum money. And therefore, I'm going to just have to help you a little bit with some very basic notions in quantum mechanics, so we're all on the same page. I assume that people know like what a vector is and know a little bit about linear algebra, but maybe don't know that much about quantum mechanics. So I'm going to start by reviewing just a few points in quantum mechanics. And for those of you who know it, it'll be very boring. And for those of you who don't, hopefully you'll learn a couple of things. So also this is an issue of notation, which I wish to establish. In quantum mechanics, quantum states are vectors in a d-dimensional vector space. A quantum state is something that describes the quantum system. And that is used, and that itself is a d-dimensional vector. It happens that in quantum mechanics, these are vector spaces over the complex numbers. So you can add vectors with complex coefficients. An important thing about the notation, so we have a vector space H. And vectors are written in this notation, which are called kets. That little thing there, that's half of a bracket. It's called a ket. And the thing inside the ket is the name of the vector. So you can write anything in there that describes the vector. So that's a vector psi. You could write dog. You could write my favorite vector, whatever you want inside the ket. It's not an argument of a function. It's the name of the vector. Okay? And so psi is an element of the Hilbert space, which, and that's what we mean by vectors. And a very simple example is if I had d equals 2, two-dimensional Hilbert space, I could have two basis vectors for the space, which I call up and down. Those are just two different vectors. They're orthogonal. And then psi, a general vector, could be a linear combination of the two basis vectors, where alpha and beta are complex numbers. And if up and down have norm 1 and they're orthogonal, then if alpha squared plus beta squared equals 1, then psi would be a normalized vector. So this is old-fashioned linear algebra over the complex numbers, but you just have to be sure that the ket, you remember, is a vector. Okay? Now, just a couple more words about quantum mechanical notation stuff before we get into it. Does that go? Now, the quantum mechanics is the description of nature at its most fundamental level. You know, you should remember that there has never been a violation of quantum mechanics ever seen. Quantum mechanics describes the theory of elementary particles. The strong, the weak, the electromagnetic force are described quantum mechanically. Everything that's going to happen at the LHC is presumably described by quantum mechanics. Well, I should say everything that's ever been seen at any existing accelerator has been described by quantum mechanics. All of chemistry is described by quantum mechanics. The entire periodic table, the properties of materials like superconductors are described by quantum mechanics. So for the sake of this talk, we are going to assume that quantum mechanics is true. And it is the fundamental theory at base which describes the world around us. It is the God-given theory. And we're not going to get into a discussion about whether quantum mechanics, you don't like it because of whatever problem you might have with it, or Einstein didn't like it. We're not going to go there. We're just going to accept quantum mechanics as true. Okay? And now, what are the basic principles of quantum mechanics that we need to know? Well, there are not too many basic principles. The first is that quantum systems are described by states in the Hilbert space. And hopefully I've helped you a little bit with that notation on my previous slide. The other thing that's important in quantum mechanics is that states evolve in time. And the evolution of states is determined by that equation I've written there, which is called the Schrödinger equation. And what it tells you is that if the time derivative of the state, first of all, I is the square root of -1. We're dealing with complex numbers here. So the square root of -1 times the time derivative of the state is a particular operator or matrix called the Hamiltonian times the state. So this is the evolution equation. It's a first-order differential equation that tells you that if you know the state at one time, you can integrate that differential equation and know the state at later times. In that sense, quantum mechanics is deterministic. If you know the state of a quantum system at an early time, it evolves deterministically according to the Schrödinger equation. What's different, this is like F equals ma, where you say the acceleration, you could write it as acceleration is force over mass. So it tells you the time derivative is something. And in different problems, you have different Hamiltonians. So if you're describing the theory of the weak interactions, you have a relativistic Hamiltonian. If you're describing the hydrogen atom, you have a different Hamiltonian. But that's specific to the situation. And part of the job in physics, obviously, is to discover which Hamiltonians govern the evolution of systems. But the basic picture that time evolution is how things occur is what we call the Schrödinger equation. And there's never been a violation of that equation ever seen. Okay, that is consistent with every observation that systems evolve according to the Schrödinger equation. Well, are there any questions? Please, it's a small group, so if you have any questions, go ahead and ask me. Okay, we're comfy with this so far? Okay, yes?
So you have the Hamiltonian as a function of time then?
It could be. It could be a time-dependent Hamiltonian. It'd be just like, just in general, it could be. It might be time-independent. Okay. But you could have, the Hamiltonian determines the dynamics, and it could be changing, right? For example, suppose, you have two nuclei, and they're bouncing back and forth like this, and you want to describe an electron going around. Well, that electron sees a time-dependent Hamiltonian.
Okay, I guess I'm wondering if...
Can you repeat questions for the VC, please?
Oh, the question is, he was curious about why the Hamiltonian could be time-dependent. It's like in Newtonian mechanics. You could have a time-dependent force.
I guess if, I'm just wondering if this is a really powerful, says something about, how they evolve. Like, are there limits on what, on the Hamiltonian, what kind of function it can be?
The question is, are there limits on what type of Hamiltonians you can have? Well, that really depends on the physical situation, whether the Hamiltonian, if it's from the point of view of this, I'm going to say no. But yes, that's a question about nature. If you say, are there limits on the form of the Hamiltonian, that's a question about what does Mother Nature choose and why. We only see Hamiltonians consistent with the theory of relativity. Why the Hamiltonians that we have, that's a question of what are the actual specific laws of nature. This is sort of the framework. Yeah.
So, does that mean that for something like quantum electrodynamics or quantum field theory, there are actual Hamiltonians?
The question is for let's say quantum electrodynamics. Yes, there's a Hamiltonian. Yes. If you have a relativistic quantum field theory, there is a Hamiltonian. It's not simple, and it's very hard to find its ground state. But yes, there is a Hamiltonian in relativistic quantum electrodynamics, in quantum electrodynamics. Okay. Now the other thing is that when you want to determine a property of a system, what you do is you measure things, and everything you measure corresponds to something called a Hermitian operator. Hermitian just means that, just a special little property. It means its eigenvalues are real. And one of the features of quantum mechanics is that when you measure a system, you measure what you can only ever get is an eigenvalue of the associated operator. That's all that ever comes out of a measurement. If you measure energy of a system, you only get an eigenvalue. That's when we learn, remember, that energy is quantized. Because if you look at the Hamiltonian that describes the hydrogen atom, the levels are quantized. And that means that not only energy is allowed, there are certain eigenvalues. And those are the only things you ever get when you make a measurement. And that's also very basic to quantum mechanics. I can't really explain why that is. I don't really know why that is. That's just the way it is. Okay? So I would now like to get a couple of consequences of this. There's the Schrodinger equation again. I wrote it. But what that tells you, since it's a linear equation, the time derivative is a linear thing, that tells you that if you integrate that equation up, the state you get at a late time, t, relative to the state at time 0, is obtained by a unitary operator. Unitary is a special type of linear operator. But what it says is that if you know the state at an initial time, and you would like to know the state at a later time, after you've integrated the Schrodinger equation, you discover that the state at a later time is simply a matrix or a linear operator acting on the initial state. Okay? Now, so quantum mechanics is linear. Well, measurements are not. So we'll get back to that. We're just talking about the Schrodinger evolution. What does that mean? What does that mean? That means that if you know the state, suppose you know that you have a system which at time 0 is psi 1, and at time t becomes psi 1 of t. Or your system at time 0 is psi 2, which evolves to psi 2 of t. Then if your initial state was a linear superposition of psi 1 at 0 and psi 2 of 0, the outcome is the linear combination alpha psi 1 of t plus beta psi 2 of t at the later time. That's what linear means. Okay? If I have two inputs, if I have an input and it goes here, and I have another input and it goes there, if I take a linear combination of the inputs, I get the same linear combination of the outputs. Okay? That's what I mean by linear. And quantum mechanics is linear. All right? We with me? That's very fundamental to quantum mechanics. There has never been a violation of quantum linearity seen. Now, we're going to use this and prove a theorem. Okay? We're now going to ask a following question. Can I copy an unknown quantum state? Can I take a state which is unknown to me, a quantum system, and make an identical copy of it without destroying the original state? And the answer to that is no. And I'm going to prove that to you right now. Suppose I would like to build what's called a quantum cloner. A quantum cloner is something that would take an unknown quantum state and replace that and a blank register. So I'm writing psi blank. I have an unknown quantum state and a blank register, or a blank state. I mean a blank, like I have two states, psi and a state called B. And I want that to evolve, according to quantum law, into psi psi. I want to copy psi into the space held by B. Okay? So that would be called a quantum cloner. Well, that's impossible, because it's not a linear transformation. That's like taking x to x squared. If I double psi, I multiply the output by 4. Okay? That's just not linear if you do that. That's like a quadratic function. So the fact is that this is not a linear transformation, and in fact this means that this is called the quantum no-cloning theorem. And it says that the quantum operations do not allow you to take an unknown quantum state and make a copy of it. And I really just proved it because it's not a linear transformation. I've argued that quantum mechanics is linear. Okay? So this is called the quantum no-cloning theorem. And this has huge implications for information security, which I'm now going to address. Because there's no such thing classically. There's no possibility of me being able to tell you that if I have a bit string, I can't make a copy of it. That's just, there's no such thing that prevents that classically. And quantum mechanically, it is not possible. Now, this actually means, since quantum mechanically you cannot copy an unknown state, this means this is called the quantum no cloning theorem. And this property allows you to send secure messages. By secure, I don't mean that they're encrypted, but what I mean is that you can be guaranteed that there's no eavesdropping. So let me show you how that works, because this is going to be the prelude to quantum money. I have not forgotten that my talk is about quantum money. I'm just building you up to it, okay? I haven't forgotten. Okay. So let's see how this works. Let's see how we're going to use the quantum no cloning to send secure messages. So Alice wants to send Bob a message. And we're nervous that there's Eve sits between Alice and Bob, and she might read the message, write it down, and then send it on to Bob. And what we're now going to show is that that cannot happen with the proper quantum protocol. Okay? So, and in fact, classically, what I mean in the absence of quantum mechanics, there's no way, there's absolutely no way to guarantee the security of a message going from here to there. There's nothing I can do that guarantees that someone can't intercept a classical bit string, write it down, and then send it on. But let's see how to do that quantum mechanically. So wait, I need to do one more little aside on a quantum measurement, which is the following thing. I already told you about this state psi, which can be alpha up plus beta down, where alpha squared plus beta squared. That's a general state. Now, we can think in this little two-dimensional Hilbert space of up being the vector 1, 0, and down being the vector 0, 1. And these are eigenstates of that little diagonal operator, sigma z, which is 1, 0, 0, minus 1. Can you all see that? If you multiply sigma z times 1, 0, you get it back. And if you multiply 0, 1 by that, you get it back a minus 1 times the state. Now, but there are other vectors I can look at, which I'm going to call plus and minus. Plus is 1 over root 2, 1, 1. And note, it's an eigenstate of that little off-diagonal operator, sigma x, 0, 1, 1, 0. You can just check that. Multiply sigma x times 1, 1, and you're going to get back 1, 1. Multiply sigma x times 1 minus 1, and you get minus the vector. Okay? Now, if you're in the up state and you measure sigma z, what you're going to find is you're going to get back the number 1. Remember I told you early on that when you measure an operator, you only get the eigenvalue? Well, if you're in this state, which is an eigenstate with eigenvalue 1, and you measure it, you're going to get a 1 and the state up undamaged. If you measure minus, if you take the state minus and you measure sigma x, you're going to get a minus 1 and the state minus undamaged. But now, if I'm in the state plus and I measure sigma z, plus is not an eigenstate of sigma z. Plus is 1 over root 2 up plus 1 over root 2 down. And what quantum law says is that if you measure sigma z on the plus state, what you're going to get is with 50% probability, you're going to get a 1 and return the state up, which is the eigenstate of sigma z. And with 50% probability, you're going to get down and the eigenstate. You're going to get minus 1 and the state down. So what happens here, if you make a measurement, is that these measurements destroy the state. Because this measurement of sigma z took the state plus, but what came out was a state up or a state down. Because I measured something, and when I make the measurement, I always get an eigenstate of the operator after the measurement. Now, let's see how we're going to use that. So now I'm going to show you how Alice can send Bob. Now Alice is going to send a secure message to Bob. Let me show you how Alice does that. Alice sends the state plus, minus, up, plus, down, down, plus. Okay? Now, Alice then publicly announces x X, Z, X, Z, Z, X. So she announces that publicly. Bob has the state, and Alice announces that string publicly. Well, after she announces it, Bob measures sigma X, sigma Z, sigma X, sigma Z, sigma Z, sigma X. And since these are eigenstates of those operators, out comes 1, minus 1, 1, 1, minus 1, minus 1, 1, because those are the eigenvalues of those things. Those are all eigenstates of these things. Okay? And that's the message. Okay? The message is the eigenvalues that she measures. Now, why is this secure? Because suppose Eve intercepts the message. She intercepts the message. First of all, she cannot copy the state because there's the no cloning theorem. She can't make a copy of it. So what might she attempt to do? She might say, well, I'm going to try to measure the different components. I'm going to see what they are. But the announcement of what the directions are has not yet been made because it's not announced until Bob gets the state. So she cannot copy the state. She only has it. If she could copy it, she'd be very well off, but she can't. So she's stuck with it. She's going to do something to it and then send it on. But she doesn't know what direction to measure in. So the first, remember the first thing she gets is called plus. So if she measures sigma X, the state plus is undamaged. But if she measures sigma Z, she gets up or down. Remember that from the previous page? So now she has this thing and she sends it to Bob. Okay? Now, if Bob gets the first bit, which is now up or down, he's supposed to measure sigma X. So when he measures sigma X, he gets plus or minus 1, each with 50% probability. So there's a 50% chance he gets the wrong answer. So what Alice does is after the bits are sent, she says, hey, Bob, certain of those bits were test bits, like the first bit was really just a test bit, and you better have obtained, plus 1 when you measured it. But there's a 50% chance he got a minus 1. Okay? And
isn't it 25%?
Fixed probability of error. Then if 100 out of my zillion bits, or if 100 out of my million bits are test bits, and there's a 50% chance of there being an error, you have only a 1 in 2 to the 100 chance that the error is undetected. So this means that after Alice sends the message and announces which are the test bits, Bob can be sure that, in fact, the message was not read. So that's huge. Yes?
There was a remote question.
Yes, I didn't hear it.
He said something about 25% that value.
Oh, yeah, 25%. Yeah, he's right. It was only 50% conditioned on, it was conditioned on something. I think he's right. It is 25%. Mine was 50 conditioned on something. Yes, it was 25%. Good, he's paying attention. Good. All right, so that's right. So this makes, and this is one of the big things in quantum information, that we have secure communication. So now we're going to use this idea to make quantum money. Okay? So let's follow the same. And this was introduced by this guy named Stephen Wiesner. This is one of the first ideas for making secure, using quantum information. He didn't have all these terms, but this is one of the first ideas for using the ideas of quantum mechanics for security. And so Wiesner's idea was a quantum money state is just going to be a product plus, up, down, minus, minus, minus. And if you have a state like that, so now the quantum money I'm going to give you is a quantum state. I hand you the quantum state. Now, this thing has the great virtue that it cannot be copied because of the quantum no cloning theorem. And measuring it will not allow you to copy it. And obviously, when we talk about money, one virtue, what do we want money to have? I'm going to talk about virtues of money. But one clear virtue we would like a bill to have is the inability for it to be copied. If I can guarantee you that a bill cannot be copied based on laws of physics, well, then I'm really offering you something which is incredibly secure. And in fact, let me just show you an example. See this bill here? This is a classical bill, and my 9-year-old son, this is a counterfeit bill that my 9-year-old son made. And it looks very good. If I pass it around, you'll see. So it's very easy to counterfeit money. This would make it through a soda machine without any problem. And my kid made it, so there is no security against. Okay, so this shows that counterfeiting is easy. Anybody wants to see the bill, I'll show it to them. Okay, so now what's the problem with this money? So the problem with this money is, as a secure form of money, is that if you want to, the mint, I give you this money, which is just a bunch of quantum state. It's just a product state. It's just a bunch of spins pointing in different directions. Now, the no cloning theorem, which we've discussed, prevents you from copying the bill. That's a good thing. Now, the mint that made the money knows that the first spin is a plus eigenstate of the sigma x operator, and the second spin is an up relative to the sigma z operator, etc. So if you send the money back to the mint can determine that it's still an unaltered money state, because the mint can check that that first bit really is an eigenstate of the sigma x operator. So if the money is sent back to the mint can verify that it's good money. So there's a picture of the bill. I forgot to show the quantum bill with all the spin states in it, which you can pass along, okay? But this bill, you have to send, it can't be duplicated. But now you send this bill, but the problem with this money is the following thing. You want the merchant to be able to verify the money without sending it back to the mint. Now, you could say, tell the merchant, you could say, well, let's let the merchant know which axes those spins are pointing along. So if the merchant knows that the first is the plot, sigma x and the next is sigma z, the merchant could measure the state and verify it. But as soon as you let the merchant do that, you've given the merchant the power to make another copy. Because if the merchant knows that the first spin is a plus eigenstate of sigma x, the merchant just can make a plus eigenstate of sigma x. And the next spin is, what would we say, an up eigenstate of sigma z. The merchant makes one of those. So the problem here is that if the merchant knows the quantization axis and the eigenvalue of each qubit, then the merchant can verify the money. So we would like so you could make another bill. That's just what this says. So what we see is a quantum money scheme with a verification procedure that does not allow the merchant to make fresh bills. Okay, that's what we want. We want the merchant to be able to hold the money up to the light and say, this is a good bill. The merchant, and still, the merchant shouldn't be able to copy the money because of no cloning, but the power of verification should not allow the merchant to make a new bill. And that's the tricky part in a quantum money scheme. That's what's hard to achieve. So what would quantum money consist of? Quantum money, each bill has a serial number and an associated quantum state that's associated with the serial number. And the mint should be able to produce bills, that is to say serial numbers and quantum states. And if a merchant is handed a bill, the merchant should be able to have a verification algorithm that takes the quantum money, outputs good money if it's good, without destroying the state. You want to be able to be sure that when you put the money into the verifier says good, but outputs the money, doesn't eat it, which is very tricky quantum mechanically, to not destroy the state. And we also want this to have the property that if I give you the serial number and the money, it is hard to make two states, psi and psi prime, each of which passes the verification. So we want it to be difficult to make a copy of, even though you have a verifier. If I didn't have the verifier, you couldn't make a copy. But then you just know you have this thing, and you don't know what properties it has. So we're going to have a little blueprint for quantum money, and then I'm going to talk about knot theory, and then we'll put it all together, okay? So here's a little blueprint for quantum money. First, imagine I have a big set, like the integers from 1 to 2 to the 1,000. Just some discrete set, which is very big. And I want to have some function, which is easy to compute, and it takes everything in the big set into some target set, and the target set is also big, but not as big as B. So for example, if B is size 2 to the 1,000, maybe the target set is 2 to the 500. Still very big. I want you to think of, 2 to the something is a big number. And I want this function as many to 1. So many things map to each target value, and I want F to be easy to compute. So this is going to be the beginning of my blueprint. So what's the blueprint here? The mint is going to make an initial state. And the initial quantum state has two parts. The first register contains a uniform superposition over all things in the big set. Quantum mechanically, it's very easy to make that. It's very easy to make like the uniform superposition of a state, which consists of all the integers from 1 to 2 to the 1,000. You can actually do that. And the next register is a blank register now, which I'm going to use in a second. The mint has a quantum computer, and the quantum computers can do anything classical computers can do. So the mint can compute the value of the function into the next register. So now my big superposition over all values of B come with an additional label, which is the value of the function. So now what the mint does is it measures the second register. And whatever the mint, when the mint measures the second register, the mint gets a value. I'm going to call that P. And so what the state is after this measurement is the sum over all values all little b such that f of little b is P. So what this money state is actually going to consist of is a superposition over all things B which have the function value P. That's what the money state's going to be. It's going to be a superposition over all things B with the value P. Okay? So now we're going to talk about knot theory. I guess I have to end at 4 o'clock, right? Because Google runs like, no? I can go on for another minute if I need to. Okay. I'll try to end at 4. Well, that's my screensaver. Well, nothing embarrassing, right? Why did it do that? Hold it. Escape? Why is it doing that? Oh, there it goes. Okay. Sorry. That's my dashboard. Okay. It's always nerve-wracking when that happens. You never know what you're showing the world, you know. I try to keep my computer very clean, but sometimes you never know. Okay, so now we're going to talk about knots, links, and grid diagrams. So now we're going to do a little bit of knot theory, okay? Not too much, knot theory. So what's a knot? A knot is a loop of string in 3 dimensions. So just think of having a loop of string in 3 dimensions. So it's a map from the circle S1 into R3. And a link is a bunch of intertwined knots. So I could have a bunch of knots which are intertwined. And if you have a bunch of knots which make a link in 3 dimensions, you can depict it by projecting it into 2 dimensions. So if I project this 3-dimensional object into 2 dimensions, I get a picture like that. And what's important about this picture is that there are arcs where you see the segments of the thing projected down, and then you have to distinguish whether a strand is crossing over or under another strand. So when you make the projection, you have to remember whether something is going over or under. And that's easily depicted in this picture here, where you see clearly that the broken piece is the over one. So that's a picture of a link. And it's a diagram which depicts the link. Okay? Now, two links are said to be equivalent if one can be smoothly morphed into the other without cutting the string. So if I have, I just want to distort the strands, the string, but I never cut it. I never push one strand through another. We could get more mathematical here in the definition, but it's just this. It's just, there's no more content to the, talking about continuous and homeomorphisms or anything. It's not going to help you. It's just smooth in this very elementary sense. Okay? Now, if two links, L1 and L2, are equivalent, it turns out they are equivalent if and only if their associated diagrams, D1 and D2, can be transformed one into the other using a set of moves called Rademeister moves. So let's see what these moves are. The first move over there, I'm not supposed to use the laser pointer. So the first move takes the green strand and shoves it under the red strand. And you can see that that doesn't change doesn't really change the link itself. It's just pushing a little piece under without cutting. The next thing you can do is you can take a strand, the green strand, and you can put a little twist in it. Well, that doesn't change it because I could untwist that. The third thing I can do is I could take 3 strands, the red one, the black one, and the green one. And note the way the green is underneath both the red and the black on the bottom part of the page. Well, I can just slide it up, the green one, so it's below the red and the black, but above the cross. Now, I hope it's clear that if you make these moves on 2 link diagrams, you do not change. When you make these moves, you're making moves that keep you in your equivalence class. Because it doesn't change, the equivalence class is all things that can be smoothly morphed one to the other. And these moves respect the equivalence class. Does that seem clear? But the theorem here is it goes the other way, which is that if 2 knots are equivalent, then the associated link diagrams can be connected by a sequence of such moves. Okay, so these moves allow you to connect any 2 equivalent links. So the point here is that if 2 links, yes? They're in the same equivalence class. What I mean is that the two diagrams represent links which can be in 3 dimensions distorted one to the other. The equivalence class is under smooth deformations which do not cut the strands. Does that seem okay? It's pretty, I'm sorry? Oh, I guess connected, yeah, in that sense, I guess so. They're connected by the sequence of moves. Okay, now. So let's take a look at this, let's look at that red circle. That's a link diagram for what's called the unknot, because it's just the most simple knot. It's just the circle mapped to the circle. It's called the unknot. But if I make a Rademeister move on it, I can turn it into that figure 8. But that's the same knot. And then I could make it more complicated, make it look more like a pretzel. Well, I could keep making these moves on it until it looked like a huge mess. Okay? I just made a couple of moves. But if I kept making Rademeister moves of the kind I showed you before, I could end up with something which would look like a huge mess, but was still the unknot. Okay? Now, so given 2 link diagrams, there is no known procedure for determining if the associated links are equivalent. There's no known procedure. In fact, it's worse than that. Known procedure for finding the Rademeister moves that take one diagram to the other. And in fact, this problem is not even known to be in NP for the computer scientists out there. Okay? It's not known to be in NP. So that means that this problem is hard. It doesn't mean that it is hard. It means that it's believed to be hard because no one knows how to do these things. So it's what I'm telling you here, the lesson of this, is if I give you two very complicated link diagrams, and I ask you, do they represent equivalent knots, you can't figure it out. And even if I give you two from equivalent knots, and I say, find the moves to take one to the other, there's no way to do that. I mean, there's no known way to do that efficiently. And that is going to be the basis of the security of our quantum money scheme. Because, you see, our quantum money scheme, since it involves something, well, let me try to, how can I say it? If you have security, if you don't have provable security, then you need to base your security on the presumed hardness of a problem. Like, for example, the security of RSA is based on the presumed difficulty of factoring. Yes?
You said it's not an entity, and you have two things up there that they seem to be saying the same thing to me, because it already demonstrated that the Radhameisters moves make it equivalent. I guess I'm asking.
Well, no. The first says I can't tell if they're equivalent. And the second says, if they are equivalent, I can't find the moves to take one to the other.
Okay.
Those are slightly different statements.
I guess but if you have two diagrams and a series of moves to tell whether or not it demonstrates that they're equivalent.
Yes, but it's not known that the list is short. I mean, for example, if you want to get into the question of NP, it's not known whether, there's no short witness. I mean, it may be an exponential number of moves to take one to the other. There's no known short witness. It could be exponential. Okay. Now, there's another thing here called a knot invariant. So there are properties of knots which are invariant under the moves. And an example of this is called the Alexander polynomial. This is a function of, you take a knot and you look at the diagram that represents it. And given that, there's an algorithm that allows you to compute a function which happens to be a polynomial. But what it really is it's just a set of numbers, which are the coefficients of this polynomial, which characterize the knot. So if I give you a knot, you can compute a particular property it has. It's called the Alexander polynomial. We're not going to use the fact that it is a polynomial. We're just going to think of it as a list of numbers, the coefficients that make up the polynomial. But it's called the Alexander polynomial. Now, if two link diagrams come from two equivalent knots, they have the same Alexander polynomial. That's one of the reasons mathematicians like the Alexander polynomial, because two equivalent knots have the same Alexander polynomial. But the converse is not true. It is not true that if two link diagrams have this, or two knots have the same Alexander polynomial, that they are equivalent. Otherwise, I could solve the problem on the other page. I would just measure the Alexander polynomial. So you can find inequivalent links with the same Alexander polynomial. And of course, if someone found a polynomial or a function of the diagram that was, one-to-one with the equivalence class, that would be huge. That would be a huge result in knot theory. So let me just say one more thing. I need something called a grid diagram. See, we work in a finite dimensional Hilbert space, and I need some discrete way of representing link diagrams so that I can encode them as bit strings. Because I need to work in a discrete space. I need to think of things as bit strings. And those pictures that I drew with those arcs and curves, it's not so obvious why those are represented by bit strings. But you can represent all these diagrams by bit strings. It's kind of easy to see why. Because all you need to do is kind of take the arcs and sort of make them horizontal and vertical and put them on a grid. And then it won't change the diagram. And in fact, if you look at this one here, look at that little two knots interlinked, I can represent that as a grid diagram like that, where I'm putting things on definite locations on a grid, and I encode the diagram by the location of the X's and O's on the grid. I've put arrows on this because these are oriented. Oriented means that each strand has a direction. That I do because of the Alexander polynomial. That's a triviality, an unnecessary detail. The point of this picture is to show you that I can make a discrete representation of the link diagram so that I can encode it. Oh, why did I do that again? How do you make that go away? Go away. I'm sorry. Hit what? Sorry. So grid diagrams are discrete representations of links. And Radameister moves, those moves, can be formulated as grid moves. But Radameister moves can change the number of crossings. Remember that when I introduced a little twist? Or when I took two things that were disconnected and I crossed them? So if you make Radameister moves on grid diagrams, you can change the dimension of the grid diagram. So for example, if I have a set of grid moves, by grid moves I mean Radameister moves encoded on grid diagrams. If I have a finite list of grid moves, they can change the dimension of the grid diagram. They can either leave it alone or they can make it bigger or smaller by adding crosses. They can make it bigger or smaller. But if you start in an arbitrary grid diagram, G twiddle, and I apply a sequence of randomly selected Radameister moves, I will end up with a random grid diagram equivalent to G twiddle. So now let me get to the quantum money. What's the quantum money? The quantum money, we start in an initial state, which is the sum of all grid diagrams, G. By G, I mean it's some kind of discrete encoding of the grid diagram, which I said I could do. And then I have an extra register. Now, I need to put a little weight function in there because the set of all grid diagrams is infinite. And I don't really want it to be infinite. So I need to cut this off in some way. And we have kind of a smooth way of cutting it off. So there's a rho function, which I need for technical details. So rho of G is a weight, which depends only on the dimension of G. And the number of grid diagrams of dimension D grows like D factorial squared. So I want to cut this off. And then what we do with the mint then takes the initial state and computes the Alexander polynomial of the grid diagram into the next register. And then the mint measures the second register and gets the result P. So now the quantum money is actually the uniform superposition over all grid diagrams with some kind of weighting with the same Alexander polynomial. So that fits my scheme. Okay, now, this is a massive sum over grid diagrams with the same Alexander polynomial. Now, how does the merchant verify the money? So, first of all, remember that I can make a move on a grid diagram and get another one. So for each possible grid moves, I could take one of these state vectors, G, and get another one, G prime. It may be the same if the grid move doesn't do anything to it, but it may change it. Now, this is now a quantum operator. So I took this classical Radameister move and I turned it into a quantum thing. Now, for simplicity, let's just take rho to be 1, my weight function to be 1. Otherwise, life is too complicated. So I put a little twiddle on my money state because I want to indicate that I've made the untrue assumption that rho is 1 for the sake of my little discussion. So the money is the uniform superposition of all grid diagrams with Alexander polynomial P. And it's not normalized now because it's an infinite sum, because I got rid of my cutoff. So, but the point thing here is that if I act with a Radameister move, I have all grid diagrams with this Alexander polynomial. But if I make a move, I get back that every state goes to somewhere else in a one-to-one fashion. So this uniform superposition of all possible grid diagrams is invariant under the move because it has every possible grid diagram in it. And the moves just take it to, it just takes each one to another or leaves it alone. So my state, my money state, is invariant under all the grid moves. And that's because it contains all grid diagrams with the Alexander polynomial, and the grid moves don't change the Alexander polynomial. So the merchant verifies the quantum state by checking that it is invariant under all the grid moves. And in fact, this, maybe I'll skip this slide. The merchant can check all grid moves at once. I won't show you how you do this. This may be too technical quantum mechanically. So the merchant can check all the grid moves at once using kind of the miracles of quantum mechanics. So he can, or she can, actually make a check where he looks at every conceivable grid move at one time. And so the quantum money state is invariant under all grid moves, and therefore, with a quantum computer, the merchant can verify that tendered money is invariant. And that means that oh man, every time I touch it, I get the same thing. Go away. So this is our money scheme. The mint can produce pairs, P, and the state $P. Each serial number is different because I don't know when you make a measurement what Alexander polynomial you're going to get. And a rogue mint cannot produce the same serial number. The reason is because, you see, the Alexander polynomial that comes out is a random number. It looks like a random string. And there's no way that a rogue mint can, given that serial number, make the superposition, excuse me, I should say we don't know how. We don't know how, and nobody seems to be able to figure out how, given an Alexander polynomial value, you can make the superposition over all grid diagrams with that Alexander polynomial. And if the mint tries to counterfeit the money by making its own, its Alexander polynomials will be different. Yeah?
How do you get all the grid diagrams so you get the same Alexander polynomial?
Because we start in the uniform superposition of every imaginable grid diagram. We then compute the Alexander polynomial to the next register. And then, so now we have a superposition of all grid diagrams, and each one has its associated Alexander polynomial. We then measure the second register. And when you make a measurement, you get one value of the Alexander polynomial, and the register just to the left of it stays the sum of all the grid diagrams with that value. I'm sorry?
Are you using sumability or superposition?
Yes, superposition, yes. Superposition, it says a superposition. So our money has certain features. A rogue mint cannot produce the same serial numbers. Tendered money can be verified. We do not know how to counterfeit the bills. And our security is based on the inability to tell if two link diagrams represent equivalent links. Yeah? A mint cannot produce two bills with the same serial number. A mint can only produce, when a mint does a production run, it gets a series of serial numbers which it cannot determine in advance. No two are the same. And in fact, in order for the money to be truly secure, the mint has to publish a list of valid serial numbers. Because otherwise a rogue mint could simply redo what the first mint did. So the merchant has to have a list of valid serial numbers. But the point of this money scheme is that the merchant never has to make contact with the mint again. The merchant is independent of the mint. No individual bills have to go back to the mint. You don't have to send your credit card number back to the credit card company in order to verify it. The merchant can just take care of it on the spot. And that's it. We made quantum money. So that's my talk. I'm sorry?
I said step 4, profit.
Profit, yeah, I don't know. That's what my family says. You know, what's the good of this? So, yeah.
Yeah, this could involve always having physical representations.
Well, that's right, but it could be that there's a quantum internet, and photons come down the quantum internet, and they appear on your, down fiber optic cables. Because there is, remember, one of the reasons I did that little introduction about secure communication is because people do send photons down quantum fibers, be sure that there's no eavesdropping, and quantum states are sent down fiber optic cables. So if you had a quantum internet, you could communicate in this way.
It would be easy for people to destroy them.
Very easy, but that, it's very easy for you to destroy money, right? I take your wallet, I can reduce its value to 0. This is not any great power I have. I could easily do it. Yeah. Yeah. No, it's really a measurement process. I was a little bit, there really is a measurement. Well, no, it doesn't change the state at all. In fact, what happens is when the money comes in and it comes out and it says good money, the money's not damaged at all. The money is an eigenstate of the operator, of the verification operator, which I didn't really show, and it's completely undamaged. You don't want the money to be damaged by the verification. So there's no damage to the money, assuming everything works. So, yeah.
Is there a way to verify without giving somebody the money? Like, there's no real way to, like, say, I have this money. Like, they don't know that you have the money until you actually give it to them, and they own it.
Well, I don't know about that. That would be interesting whether, you could say, I have, I want to convince you that I have valid money, but I don't hand it to you. I don't know. I'm sorry? I see. It's just saying we should be able to verify the money before I hand it to you. I could have an escrow account. There could be a quantum, there could be trusted parties. I could set up a business. Maybe this is how I'll make money. You hand me your quantum money, and I will verify that it's quantum money, and you pay me to verify that because you don't have a quantum computer. And then I pass it back to you, and if it's no good, I can say, don't deal with that guy. That's a money-making scheme. Go ahead.
Is there a way to have a data payload associated with your serial number?
A data payload?
I mean, is there some data associated with your serial number?
Oh, yeah, but it's not that big, right? Because, suppose I have a zillion bills, and each one has a serial number that's, 10,000 bits long. Still pretty small. I think the database of all bills with their associated security numbers is quite small. We could also use some kind of public digital signatures. We could also probably use digital signatures where you could compute some if we needed to. I'm sorry, I lost the mic.
It's still attached to your little
Oh, okay. Well, I'll hold it then. Okay. Can you still hear me remotely? Yeah. They left. Yeah. Okay. Go ahead. All right. Are there any other questions? Huge superposition. That's what makes it hard to make. If it was a small, you see, if I give you an Alexander polynomial, I can find a graph, a grid diagram that represents a link with that Alexander polynomial. What's very hard to make is the huge superposition. I mean, making huge superpositions over things is for people who know a little bit more about quantum information, that's a very desirable thing to be able to do. Like, for example, if I give you do people know what the graph isomorphism problem is? The graph isomorphism problem is the following problem. I give you two graphs, and I ask you whether there's a permutation of the vertices of one graph that turns it into the other. Now, that problem is actually easy on average, but there's no known algorithm that will solve it in the worst case. There is a very simple quantum way to do it. And the simple quantum way to do it is if I gave you a graph, I don't mean to actually do it. There's a simple idea which, if you could implement, would do it. Suppose I gave you a graph, and I gave you, and I could turn the graph into the superposition over all permutations of the graph. Well, if I give you another graph, and I turn it into the superposition over all permutations of that graph, if those two graphs are isomorphic, then those two superpositions are the same, because it's all permutations of the graph. So two graphs which are isomorphic map to the same two superpositions, and you can always check if two vectors are the same. So if you could make a massive superposition over all permutations of a graph, you would solve graph isomorphism, and nobody knows how to do that. Making massive superpositions is difficult. Now you could ask, why didn't we make our money using the inability to make that superposition for graph isomorphism? And that's because graph isomorphism is easy on average.